Okay, so yesterday we finished with this big picture. So we are in the proof of the triangular prism equation in general, at least the bigger generality in this paper, but I expect something even more general, but that was not required for this paper. So we proved yesterday the left-hand side. So we have the monoidal triangular prism evaluated by two ways. So the left-hand side only involve the use of lemma 3.2. So you can see the triangular prism. You can see it with this global form. And so you apply, you have the basis, etc. Here the bases are called B0, and the elements of the basis are beta 0 and beta 0 prime. So we apply that and we get this form. And then you just have to deform this picture using zigzag relation to get something closer to the monoidal tetrahedron. And you finally need to apply some natural isomorphism rho and sigma. In fact, in here you just have a rho, in fact no sigma, to get exactly the shape of a monoidal tetrahedron. So now the right-hand side. So here is another global view of the monoidal triangular prism. And for the right-hand side, we will apply the resolution of identity 3 times here, here, and here. So the resolution of identity was stated and proved as a proposition 3.8. And so remember, the basis involved in this proposition was in fact a composition of bases from the basis is lemma 3.6. That is why we realize this resolution of identity using this basis, and this basis here look complicated. It's a composition, but in fact, if you go to proposition 3.8 and lemma 3.6, this is exactly what we get. So you just see this global view. You replace every identity here by a sum, such sum with this basis, and what you get is exactly this picture. So there is no thing complicated. The only thing which is complicated here is to draw the picture. Otherwise, it's just a straightforward application of what we did before in section 3. So yesterday I drew the picture quickly, so I was not able to do something very clean, but I repeat again. There is no crossing, nothing touch. So there is no string who touch who cross here. And every such string should be represented as identity or evaluation map or co-evaluation map, etc. So you have some zigzag relation everywhere. So this picture is well defined in the categorical framework. Okay, so now what can we do with this picture? We need to cut it into 3 parts to recover the monoidal tetrahedron. In fact, you should observe so here you have S1, S2, S3, and so for example, so let me write it. observe that above picture is of the form, the following form. So you can group, so from A, you have S1, and you have a B, S2, you have a C, S3, and a D. So I will show you what is the I, B, C, D in the picture. So I will explain for A, and you will understand similar for B, C, D. And you have this trace, some sense. So what is A? As I said, you have S1 here. And you have this S1, and then you have something like that. So A is everything which is in between S1 and these two co-evaluation map. So this co-evaluation map are this one and this one, if you want. So A here is that, if you like, this, like that. This is A. Then you have this move, and here you have this. So yeah, this move, and everything is connected only to the rest only by S1. So this is A, this group. So you put everything here, and you really have something like that, and S1. Similarly, B is everything which is between S1 and S2. So how to like that, like that, like that, like that. This is B. You have S1, S2, and you see there is nothing crossing this area. So this is really except S1 and S2. So this is really B, and etc. You have C, D. So you have this shape, but this shape now is very easy to. Ça marche le son? Hein? Le son marche bien. This shape is very easy to cut into part because S1, S2, S3 are simple objects. So this is a morphism between two simple objects. So it is zero if the two simple objects are non-isomorphic, and this is a multiple constant of the identity if they are isomorphic. So that can be directly break into three parts. So let me write. So where Si I equal 1, 2, 3 are simple object. By Schur lemma, it is non-zero. So what is non-zero? So this picture here interpret as a non-zero scalar. It is non-zero if up to isomorphism you have S1 equal S2 equal S3, and we use a notation X, so equal to point. This is the symmetric of two. So this means this is how you define X. So as I said, by Schur lemma, to be non-zero, you need that equal that, and you need that equal that. So up to isomorphism, they are equal. So they should be all equal to be non-zero. So now you can replace it is zero, or if it is non-zero, you can replace everything by x. And so so in this case, the non-zero case, it is equal to the following picture. So you can cut it into 3 parts using the lemma 2.9. So I will recall it is equal to the following by lemma 2. I don't know if we say lemma or lemma in English. Lemma? Lemma. I will say lemma. Anyway. So lemma, so recall this lemma is if you have something like that, with x simple, this is equal to dimension x inverse trace of alpha times identity of x. So remember, to get such result, to apply the Schur lemma in the usual sense, you always need the field to be algebraically closed. Otherwise, the end of between 1 and 1 is just a division algebra, not necessarily one-dimensional. So, field algebraically closed, this is important assumption. Okay, so you apply this lemma 2.9 here. So you can apply it here, then here. You can apply it 2 times. 2 times. You can apply the following, call to the following by apply 2 times. 2 times. Okay. So you get 2 times. So you get 2. So dimension x power minus 2. You get the trace of that, and identity. So it remains only this up and multiplicative constant. So it is equal to. So let me say this is equal. So dimension x by power minus 2. A d identity of x, and these 2 years. Okay. And the trace. So trace of B, trace of C. Okay. So, so now you have 3. You have a constant, and you have a 3 part. These 3 parts will be reformulated into 3 monoidal tetrahedron. So this is up to reformulation. This is the right-hand side of our equation. Okay. So just a small remark. Here we have pivotal structure. And here, so what mistake? This is power minus 1. Okay. But you have trace. If you remember the definition of a trace, the definition of a trace involves a pivotal structure. In fact, that will vanish, that will delete 2 of this pivotal structure. So when you apply this formula to the big picture, there will have no more pivotal structure here, and you will keep 1 pivotal structure here. So let me just write it here. Not that. The trace will simplify 2 pivotal structure. The trace will, the traces simplify 2 pivotal object, in fact. Object, the 2 trace. Yeah. So 1 point and the other point here is so this 3 component will be reformulated as tetrahedron, as monoidal tetrahedron. Monoidal tetrahedra, for the plural, of our right-hand side. Okay, so let me write these 3 components explicitly. So then, and you have here also dimension power -2, but here you have dimension power 3. Remember, S1 equals S2 equals S3 equals X. So your dimension X power 3, dimension X power -2. So it remains only 1 dimension X. Dimension X power 1. Then TP is equal to the sum for X in big O. So remember the definition of big O. Big O is the simple subobject, the set of simple subobjects up to isomorphism, which are the set of simple subobjects of both Y1 star, Y2 star, Y3 star. Let me go to the definition here. Big O is a set, and this is exactly what we get because S1 equals S2 equals S3. S1 is the subobject of that, S2 is the subobject of that, S3 is the subobject of that. But if you don't have the equality between S1, S2, S3, as we said, up to isomorphism, it is 0. So we only keep the non-zero summand, and the non-zero summand correspond to the simple subobject of both this one, and this one. So the set of possible this simple object here is by definition big O, and so this is why we write X in big O here. Okay, and then you have the usual basis. I equal 1, 2, 3. So this basis, I guess we already mentioned. Yeah, so this is already here. Okay, so here you have X. You reduce to X in big O, because otherwise it is 0. And you get that, and that here is dimension X power 1 now. Dimension X power 1 times the following picture. So we will start by this one. So A, D. So you will, as we said, A involve this only this morphism, but D involve all these three morphisms. So you will have something close to a monoidal tetrahedron involving these three, these four morphisms. And you will have this pivotal structure because you take it from here. So you keep it. This one will not be. Only this one and this one will be simplified. And this one will appear. So you get the first picture like that. Beta 1, beta 3 prime, A inverse X, alpha 3, alpha 6. That. So this go here. Okay. This one go here. And the third one will go there. Okay, now this like that, and this like that, this like that, and this like that. Okay. So let me write the object with another color. X6 here, X8, X3. So in fact, the picture to be completely defined, you don't need to write the object because the object already included in the definition of the morphism. So only the morphism are required, but this helps to understand. Okay, so this is really what we have. In fact, we have these three parts: alpha 3, beta 3, prime alpha 6, alpha 3, beta 3, prime alpha 6, corresponding to D. And for A, we have beta 1 and that. So S1 equal X. So you have that directly. Okay. And you do the same for the two. So yeah, you have that. And then for the two other B and C, you apply the trace. So remember, we say C is here, like that. No, this one also should include. So something like that, including that. Wait, I'm taking too much of beta 1. So S1 is here. So it should include this one, this one, this one, and go up to wait, how many you need? 1, 2, 3, 4. Let me check. Trace of B. So 1, 2, 3, 4. So that should not be inside. Yeah, so like that. You don't take it. Okay. Okay, like that. Okay. So this is B. And the trace. So, okay, now B. Okay, so you have the trace. So you just do that. So you have the B, you have this one here and this one here, and you're just doing like that. So if you draw explicitly, you get the following. Beta 1 prime, beta 2, alpha 4, alpha 1, and remember the trace in the definition of trace, you have a pivotal structure, which cancel with, as I said, with this one. So you don't need to write it again. This you have the trace, and this trace involves some pivotal structure again, which will cancel this with the other. So you can draw the picture without any pivotal structure. Okay, so this one, like that, like that. Like that, and this one. Okay, let me draw the last one here. That. Oh, this one is very complicated. Then we will go to the first leg of beta 2. And the second leg of beta 2 will go to the third leg of alpha 4. And we're done. So here it's x, x4, x9, x1. Okay. And oh, I have no place, I have no room. I have to change the page for the last one. I cannot make it small. So for the last one, same idea. Or maybe I can just draw it small here. Let me see. I will try. If I short this one, then I can move this a bit. Oh. And then I have space for making. So the same idea. I will make it smaller. So alpha 2, beta 2 prime, alpha 5, beta 3. So here the picture will not be nice, but it's okay. In fact, this is exactly the same as before. Up to yeah, this is the same picture as before, completely similar. In fact, the same picture, you just have to replace alpha 1 by alpha 2, beta prime 1 by beta prime 2, alpha 4 by alpha 5, beta 2 by beta 3. And the object alpha x4 will be x5, x9 will be x7, x2 will be, no, x9 will be x7, and x1 will be x2. So the same. This one will move to the first leg as before. That this one will go here. This one. Yeah. And finally, this one. So now the picture is not nice, but it's okay, the same as before. Okay. X5, X7, X2. Exactly the same as the second one, up to changing morphism and object. Okay, so the same. It is the same because it is the same process, trace of C, and C here appear. The C part here is very similar to the B part. So the similar part, similar process. So you get a similar picture here. Same picture of two modifying the morphism. Okay. Okay. So let me. It remains 12 minutes before the break. And so now you just have to apply some zigzag relation and some natural isomorphism rho and sigma to recover the exact shape of a monoidal tetrahedron. And we will need also to move this pivotal structure here by applying the lemma 2.5 because this is the definition of sigma, the natural transformation sigma is something like adding a pivotal structure. So we move this here, and then you have some rho you have to consider, etc. And to recover the exact shape of a monoidal tetrahedron. So after applying some zigzag relation lemma 2.5 to move the pivotal structure, as I said, and pivotality. Pivotality is for what? So pivotality will be used to what? Yeah. Maybe when you involve, for example, you apply 3 times the natural transformation rho, it's like doing the double dual. And the double dual is related to the definition of pivotality. So maybe to simplify, you need this need to involve the double dual and the definition of pivotality somewhere. But this is okay. We get the original form of monoidal tetrahedron. So TP equal sum for x in big O sum for beta I in bi I equal 1, 2, 3, dimension x times three thing. So so something like that. So rho of alpha 3, rho square of beta 1, rho inverse of alpha 6, rho power minus 2 of sigma of beta 3. So like that, like that. Wow. So that here, here. So you see now I am drawing very quickly. Okay. So this is the first one here. So you have the sigma beta 3 prime coming from moving the pivotal structure. You have that here. And then you need to consider some rho to recover the exact shape, etc. So this is straightforward now. So alpha 1, beta 1 prime, beta 2, rho prime alpha 4. So then this is exactly the same shape. And no place, okay. No room. And so alpha 2, beta 2 prime, beta 3, rho inverse alpha. That, like that, like that, and finally this one. Okay. Okay, so just yeah, you observe these three pictures, and you observe these three pictures, and you understand that up to this. So by applying this natural transformation, you get the same picture. But these last three pictures are the exact shape of a monoidal tetrahedron, so that can be replaced by formula T of so the T of 1, 2, 3, 4 morphism times T of etc. etc. So and so you get that the TP is, you get the right hand side. Sum for x in big O, sum for beta I in bi, I equal 1, 2, 3, dimension x, t. So the first one, remember The morphism are ordered. So the first here, second, third, fourth. So T of rho power minus 2 sigma beta 3 prime rho of alpha 3 rho square of beta 1 rho inverse of alpha 6. So don't have enough space. Okay, T of rho inverse of alpha 6 times T rho inverse of alpha 4 rho alpha 1 beta prime 1 beta 2 times T of rho inverse alpha 5 alpha 2 beta 2 prime beta 3, which is the right hand side, what we wanted to prove. So we are done with this first version of the triangular prism equation. We proved the left hand side yesterday, the right hand side today. So now the next step of the course will be to simplify the picture by adding extra structure, like sphericality, to get proper to make sense of the triangular prism equation involving this kind of picture. So I guess it's a good time for making the pause before the next section. So 6, let me say 4, 6, 9. Ok, tu peux faire la pause. Okay, so so we finish the proof of the triangular prism equation, left and right hand side. Now we will start a new section. So the goal is to simplify the picture. And what will help us to do that will be an oriented graphical calculus. Oriented graphical calculus. Wow, ça marche. Oriented graphical calculus on pivotal fusion category. And then next we will move, next section we will move to spherical, and we will be able to consider the usual form of a tetrahedron in the framework of monoidal category, a fusion category. Okay, so this section will be, in fact, yeah, I guess we will finish today by this section. It will be, as hard to say, a break after the section 6 with all this bigger picture. This section will be easier for me. So this section, this section was inspired by a paper of Bartlett published in 2016. A paper of Bartlett in which he discussed the oriented graphical calculus. So we did not strictly follow his notation and his result, but we went through his paper and we created our own notation, which is more appropriate for our need. but it's very close to what he did in his paper, so it deserves to be cited. It was inspired by paper of Bartlett 2016. So let's see, be a pivotal fusion category. Let's see, be pivotal fusion category. Let A be the pivotal structure. Let X be an object in the category, and we will define the oriented co-evaluation and co-evaluation map. Let X be an object in C. We will define oriented evaluation and co-evaluation map. So, evaluation or co-evaluation. Evaluation maps. Co-ev X, and the orientation will be correspond to a plus or a minus. Okay, so first, the plus version will be the version already defined without this extra index. So ev X plus will be just what we define as evaluation map for X. So this is a map in the home space of morphism between X star tensor X to 1. Co-ev X plus is also the same as before. So between 1 and X tensor X star as defined in section 2. As defined in section 2. Okay, now the minus version. Next. So ev X minus will be defined as follow. AX. So you need the pivotal structure. X double X only star, and here you have evaluation map, identity, pivotal structure. So if you like, you can write it with a formula. Evaluation map of X star composed with pivotal structure, tensor identity of X star. Okay, so it's an element of this space. Okay. Similarly, for the minus, so this is like that. X star X, which is identity of X star tensor pivotal structure inverse composed with the co-evaluation of X star and its element in this home space. 1 X star tensor X. Okay. So first observation, the usual evaluation co-evaluation map. Evaluation of X star tensor X to 1. For the minus version, it's X tensor X star to 1. Similarly, here, the usual co-evaluation map is from 1 to X tensor X star. And for the minus version, it's for 1 to X star tensor X. So you just move the star to get the good home space of the minus version of this map. No. So what we are interested in here is to simplify the notation using some arrow, some orientation. So let us depict this morphism as follows. So have X plus will be this one, this arrow. Have X minus will be the same shape but with the opposite arrow. Co-have X plus will be like that. Co-have X minus will be like that. Opposite arrow X. So the position of the X correspond to. So X here it is the X, here it is the X object. So here object X. Here it's here. So you cannot write the X here. Yeah. Okay. So the plus version, in fact, are exactly what we drew before like that. But you have the minus version. So to distinguish the two, we use this opposite arrow. And we can also use an oriented notation for the identity. You have the usual identity of X, and identity of X star will be defined with the opposite orientation by keeping X in the picture. So let us also use the following notation. So this is that which is identity of X, and the opposite orientation is, by definition, the identity of X star. Okay. So, according to that, so you don't need to care about. You no more need to consider the dual. You only need to change the orientation. Okay, and now we will prove the oriented zigzag relation, which is straightforward, but this is our straightforward part. This is a straightforward section. Relations. Okay. So following above notation condition and above condition notation. So I will write this this sentence for most of the coming result. By that I mean, I did not rewrite let C be a pivotal fusion category, let A be blah blah blah, let X be blah blah blah. So this is this condition and this notation. By notation, I mean this notation. So we use this notation and this condition, and we get this oriented zigzag relation. So something like that. So here, so X here, which is like that. So here you have the oriented coevaluation map, identity, oriented evaluation map, identity. It is equal to just identity. And also equal to something like that. X. Okay. And same thing if you take the opposite orientation everywhere. So opposite orientation. Tac. Here. 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 Now the X is in the middle. So there is a kind of logic here. Here the okay. So here you see the arrow is going this way and it continues to go this way. So there is no, you don't have something like that where one is like that and the other is like that. They always go. So if you think about something, a time, the particle move in this direction or here in this direction. And so here is also the same direction from top to bottom, top to bottom, top to bottom. So there is a logic, this is coherent. Bottom to top, bottom to top, bottom to top. Okay. And the proof will be straightforward. You just have to write the definition and to apply some zigzag relation or simplification. And there are something which is even simpler is the first, this equality and this equality, in fact, are exactly this orientation is the plus orientation. Plus. So, and this is identity. So this equality and this equality are exactly the usual zigzag relations. So we only need to prove this one and this one. So the first and last equalities are the former zigzag relation. Zigzag relation. So see the section 2. about the two other ones, so you just need to write the definition of the minus version, and you will get directly what you want. So this one is, so definition is like that. So the oriented, so you have the oriented evaluation map, the minus version of evaluation map, it's like that. And then you have the negative version of co-evaluation map, which is like that. So if you use the usual zigzag relation here, you can make a first simplification. Usual zigzag, you get something like that. But now you can simplify. You get that X, which is by definition what we draw like that. So this one is okay, and the other one is even simpler. But yeah, it's symmetric. So like that, like that. X is here. So in fact, in this version, the two pivotal structure are already in the middle and can already simplify. X star, X star. So this is like that. X star, X star, which is identity of X star by the usual zigzag relation, which is by the previous definition, like that, previous notation. So X star, like that. So everything works as expected. We can also provide a simplified version, a simplified pictorial way to pictorial dimension. So the dimension before was defined using the trace, which was defined using the pivotal structure. But using this oriented notation, you can get a picture for the dimension without pivotal structure, without depicting the pivotal structure. Just a oriented circle will be enough. So as before, following above condition and notation, above condition and notation, we get that this picture, if you consider like that, so this means one co-evaluation map oriented like that, and you compose with one evaluation map oriented like that, so you have something circular. So yeah, there is no opposition. You don't have that and that. This makes no sense because we will be we'll have an it is really, yeah. So this is a dimension of X, and this one, so the other orientation, will be the dimension of X star. Here the X is here. Here the X is here. Is the dimension of X star. Okay. We try to make better circle. Okay. Okay, so proof. The proof will be as straightforward as before. By definition, so we use the definition of the trace definition of the dimension and the lemma allowing us to have the trace where you put the pivotal structure on the other side. Remember, the trace is defined. You have some, so you have trace of alpha, you put a pivotal structure and do like that. But you also have alpha star pivotal structure like that. Remember that. Something like that. And we will need this other version for this one. So the trace definition of dimension, and this is the trace other side. Okay. So you have this by definition is which one is the plus? The plus is from right to left. So you have that, and this one will be the minus, which is by definition something like that. Okay. And here you have X. Here you have X star, which is the trace by definition. This is a trace of identity, which is by definition the dimension of X. So here we don't need the lemma, but for the other one we will need the lemma. Tac, tac. So from so now you have that, and here a x minus 1, like that, x star x, which is the trace of identity of x star. So using this lemma. And this is the trace of identity. So wait, here's the lemma, it said it's like that. And this is exactly like that by some other lemma I forgot. And this is the dimension of x star, which is what we wanted to prove. Yeah, so we prove something like that. The trace of identity, you can move the dual here. we prove that. It's okay. Okay. So now we can provide also the oriented version of the statement about applying the dual for evaluation and co-evaluation map. So following able condition and notation. The evaluation map X plus or minus star is the coev X star plus or minus. So you keep, this is exact, so you replace the X by X star, but you keep the orientation. You keep the plus, you keep the minus. And coev X plus minus, as you can expect, is ev X star plus minus. And the proof is also straightforward using zigzag relation, etc. So proof. So first, the statement with plus is exactly what we proved before in section 2. The statement with index plus everywhere is exactly statement. Is exactly lemma 2.2 we prove in section 2. Now about the minus version. This is so evaluation X AX. Now you apply the dual. So the dual you move, sorry, you move that like that, and here you have identity like that, but you don't draw it. So it is just like that. But you have a zigzag relation here. So you only need something like that. Zigzag relation. Which is, remember the lemma which move the pivotal structure from one side to another side. We prove the lemma like that. But this is nothing but the co-evaluation map of X star minus by definition. If you don't trust me, you can come back to the definition, which is here. Okay. And same for the other. Co-ev of X minus star is so AX, so something like that. And I forgot. Wait. Yeah, it's okay. And then the star. So you apply zigzag again here. So you get only that. X. And this is, again, by the previous lemma, 2.5, like that. lemma 1, 2, 5, which is the evaluation map X star minus. Okay. So we are done with that. So it remains 13 minutes. Okay. So we're almost done with this section. Oh, it remains something. Okay. It remains a result involving the second formulation indicator. So maybe we'll have time to finish this section today. So before that, there is a remark. The following remark about, so by using the previous result in this section, in fact, you have no choice. You have not too much choice about the definition, about how to take the morphism and co-evaluation map and evaluation map. In fact, the only variation you can have is just multiplying by a multiplicative constant and the same multiplicative constant for the 4 map. Sometimes it is k, sometimes it is k inverse, but you only have one dimension of freeness here. If you want to twist or to modify the evaluation and co-evaluation map. So remark. And if I am not mistaken, this remark will be used later, I'm not sure. So let X be, so in the simple case, let X be a simple object in a pivotal fusion category. Fusion category. So by EGNO book proposition 484, we already cited the dimension of X is non-zero. Then by the previous lemma 7.1, 7.2 from this section, the choice of the 4 above morphism evaluation and co-evaluation map plus or minus are unique up to a multiplicative constant. The choice of the 4 above morphism so co-ev X plus or minus is unique up to a k, a non-zero k. So this morphism, when X is simple, in fact, they are just element in some something like that, or something like that, or something with a star here or here. So these home spaces are one-dimensional. So they are. So you can say, okay, you can fit. This is well-defined. This is defined up to 4 constants. But in fact, these 4 constants are related to each other by this lemma. So in fact, the only liberty you have is to do like that. K F X plus K F X minus K inverse O F X plus K inverse coev x minus. Okay. So the small remark perhaps we will use later, I don't remember. And so the last statement of the section involve this evaluation and co-evaluation map and the Frobenius-Shaw indicator, the second one. When X is self-dual, you can go from the plus to the minus version of this map by multiplying by this second Frobenius-Shaw indicator. So lemma 7.5. So as before, following above condition and notation, if X is simple and self-dual, then the evaluation map negative version is the plus version up to multiplying by the second Frobenius-Shaw indicator. And same for the co-evaluation map. Coev x minus is second Frobenius-Shaw indicator of x, coev x plus. Okay. And so proof. So Frobenius, let me write second Frobenius-Shaw indicator. So the proof is the following. So because X is simple and self-dual, the Hom space between X tensor X to 1 is one-dimensional. By assumptions on X, Hom C X tensor X to 1 is one-dimensional. In fact, maybe it will be enough to just say this as an assumption here. So just to say this, it's more general a priori than that. A priori. But maybe we need the simplicity also, I'm not sure. Because we will need the proof, we'll need the lemma 216. And the lemma 216 no, we don't need simplicity, so I guess. In fact, you can replace this condition by this condition. This is a little bit more general, but does not matter too much here. So by assumption on X, we have that which is one-dimensional. Okay. So evaluation of X minus is by definition AX is like that, which is we will write explicitly the identity, and then we apply the lemma 216 with kappa. So this lemma involves some morphism kappa, and with kappa equal identity. With kappa equal identity of X. And we can apply this lemma because of that. This lemma need this assumption. Okay. So this lemma is saying that you can move kappa on the other side, and you remove that, you move kappa here, and you put some formulation indicator. So this is exactly what the statement of lemma is saying. But this is equal to O2 of x evaluation map of x plus, because here this is just identity. So you just have the usual evaluation map and x star equal x. So x star equal x. Oh yeah, so here you need x star equal x, in fact. So maybe you cannot, yeah. You can have something more general, but you need to put a star. You need a star if you want the statement more general. Anyway. Okay, and we will finish with the second minus, which is equal to coever x star minus, because x equal x star, which is equal to evaluation x minus star by the lemma we proved recently, and by above, by the previous line, this is equal to second formulation indicator of x evaluation x plus star, which is second formulation indicator of coev x plus by again by lemma 2.2, and that's all. So this is what we wanted to prove, and so we are done with the section 7. So next week we will start section 8 about oriented monoidal tetrahedron and spherical triangular prism equation. Okay, let's stop.